event counting with the NI USB 6211. We'll get into programming this with LabVIEW graphical programming in just a moment, but first I would like to show you our hardware setup. Here we have the USB 6211. This has two 80 megahertz counter timers on it. We'll be using those to count events. Our events today are going to come from this Hall effect sensor right here. The Hall effect sensor will act as a switch opening and closing when magnets come into proximity to it. So we'll get to that in just a moment. But first, we're powering the Hall effect sensor with 5 volts from the USB 6211. It comes back here to ground into the unit at this point, and then the pulses that come out of the Hall effect sensor come into counter 0 right here. When the Hall effect sensor closes, it will ground this input or give us a logic low. When it's open, we'll hold it high with this resistor, this pull-up resistor right here. Now, inside this small motor housing, we've placed 2 magnets, and as these spin around, they're going to create events or closures with our Hall effect sensor. We wanted to be able to generate higher speed events, so we put them inside a motor housing that we can spin at a pretty reasonable rate. We're going to control the speed of this motor with this power transistor here that modulates the power of these batteries to the motor itself. And then finally, the analog output from the 6211 will control that power transistor and allow us to directly control the motor speed. So that's our hardware setup. Let's get into programming this with LabVIEW. The first thing that we would like to do is put a slider down, and we're going to use this to control the speed of our motor. So we've experimented around and we've realized that the range for output that's best for this motor right here is 6 volts output on the analog output, or 0.6 volts, to 0.75 volts. The next thing that we want to do is put a gauge down, and we're going to use this when we're acquiring our count values to see what those values are. So we'll put this up about 50 events per second. Let's now go back into our diagram. The first thing that we're going to do is bring down a DAC assistant, and we're going to use this to set up our analog output to control the speed of the motor. So here we're going to generate signals, analog output, we'll choose voltage, analog output channel 0, which is this channel right here in our setup, and now we'll just set up some of the things that we need to in here. Basically, we need to tell it to generate 1 sample on demand, and that means this is a software timed output, and it'll update a new value every time the loop cycles 1 time. Okay, so the next thing we need to do is wire up our slider into the DAC assistant. At this point, we're ready to go and read our events, so we'll need another DAC assistant to do this. We'll place a DAC assistant down on the diagram. We're going to choose acquire signals this time, and here we would like to acquire counter input. Now we want to count frequencies, or measure frequency, and that'll come into counter 0. And at this point, we can go and set up what we need here. It's 1 sample on demand. Everything is set up the way we would like it, so let's click OK. So at this point, we've set up our counter to read our events, and now we need to wire this over to the gauge. One thing I'd like to do, though, is make sure that I set the speed of the motor before I begin counting, so I'm going to wire the errors from the DAC assistant analog output into the counter timer to make sure they happen in the right order. Okay, so the next thing that we would like to do is wire something called the timeout. When we're counting frequencies, you could have a very long event, so it needs to know how long you want to wait before you've decided that it's not actually going to generate an event, like maybe it is stalled. So we'll just give it a value. We'll wait a maximum of 10 seconds, and if we don't get anything, then we'll assume that it's not spinning. Okay, at this point we'd finally like to put down a loop. So we'll surround our whole thing with a loop. And then what we're going to do is create on the front panel a control that will allow us to shut our program off. Now the last thing that we would like to do is make sure that when we stop running our program that our output to our motor goes to 0. So we'll put down one final DAC assistant, another analog output, so we'll generate signals, analog output, and voltage. And at this point we're going to go ahead. Everything is set up the way we want it there, except we need to tell it 1 sample on demand. And we're going to make sure that this outputs a constant value of 0, and that means our motor will be shut off. So we'll create a constant. There's our 0 value. That's all set up and ready to go. We'll make sure that this happens right in the order of execution. So we're going to wire over our error right to the input on our DAC Assistant, and now that ensures that that shutdown will happen as the very last thing that happens in our program. So that's our program, and we're ready to run it. So we come to our front panel. Now, one thing that we know is we want this to be spinning so that we can count it. Otherwise, we'll be sitting there waiting for this event to happen. So we're going to give it an initial value of about 0.75 volts, and this should get the motor spinning pretty fast, and then we'll come in and throttle it down. What you'll see now, when we run it, the motor takes off and spins, and then we drop that slider down quite a bit, and then you can see that our gauge responds nicely. So if we drop it down a little bit more, you can see that it throttles down and it's counting the events very smoothly, very nicely. So as those magnets spin in front of that Hall effect sensor, at this point in time we're getting 35 events every second that are being counted very nicely, and it matches perfectly with what the RPMs of the motor are. And you can see that our analog output gives us some very nice control over the speed of that motor that we can detect and count as events. So at this point we'll hit our stop button. We know that that goes in and generates a 0 out and it shuts the motor off. So our setup has allowed us to do our analog output to control something, but importantly use those 80 megahertz counters inside the 6211 to count those events from the magnet off a very speedy device, the Hall effect sensor. So this is how you do event counting with the NI USB 6211.